Welcome everyone to the second topic. In the first topic, we have seen what indicial notations are and what tensors are and how indicial notation helps in simplifying certain calculations. So now that we have covered the basics of it, we will now start with the applications of the same. So we'll start with this definitions of strain. So what exactly is strain? Strain is one measure of deformation. When you have deformation, you can measure it by various, you can quantify it by various means. And one such measurement of deformation at a point is called as strain. Okay. So before we get into what exactly what is the mathematical definition of it, let us review what our understanding of motion of a body or displacement of a body is. So there are two kinds. One is rigid body deformation, rigid body motion, right? And in rigid body motion, the object can rotate or translate in any of the three directions. That it can translate in three directions and it can rotate in three directions. This is assuming that that there is no relative deformation between points on the same object, right? So, and then there is deformation, right? So the displacement of a body or the motion of a body can be quantified into two ways or can comprise two things. One is deformation, one is rigid body motion. Okay, and the deformation, you can quantify it as change in distance between 2 points or change in angle between two particular line segments. And often the practice is that you pick two perpendicular line segments. All right. So this is sort of what happens when a body is being displaced. When a body is displaced by a particular amount, then part of it could be deformed and part of it could have been accounted in rigid body motion. All right. So this is what happens when you say there's a body and it is being displaced. Okay, this is the reference axis. So during this displacement or during the motion, it could have underwent deformation or rigid body motion. And in that, it can have any of the four combinations. All right. So again, the deformation, rigid body motion is something which you all are familiar with. Again, the deformation can be small or can be large. For example, the deformation which happens when we sit on a chair, the deformations that the wood in the chair undergoes are very small as compared to the deformations which occur in a chewing gum. The deformations which occur in a chewing gum are called as often large deformations or finite deformations. The deformations which are happening on the door, on the chair, on the shelves are all small linear deformations. You place a bunch of books on a shelf, the shelf does deform. It is not visible to the naked eye, but it does deform a bit, which the calculations of which you have seen in strength of materials. So those kinds of deformations are called as small linear deformations. They're small and they're also linear. And since most of our displacements are small, we also call them as infinitesimal deformations. Infinitesimal deformation implies linear. We are especially concentrating on small linear deformations. And since in that, when we say small, they're actually very small. Hence, we will use the term infinitesimal, which is very small linear deformations. Right. So please draw the diagram and I will walk you through this figure. So there is one object which is shown in this dotted line. There is no concept of time. We are just dealing with, there's a object, it has, and in the next stage, it has underwent deformation. So we are dealing with two static states. This is the initial state where the dotted line shows the object, it represents the object. I have the origin O. And if I pick a point P0, the coordinates are x0, y0, and z0. And there is another point which is at a vectorial distance of dr0. The point P has a position vector r0, and from point P, I have a small distance at a small vectorial distance dr0. I have another point Q. All right. Now, this is the initial state, and by some means it has underwent deformation. Okay, it underwent some motion, some displacement. Okay, this is the initial state, and it has underwent some displacement. So this larger object is the final state of the object. Originally it was small, it had some shape. Now this is the shape it has. Okay, and we had 2 points P0 and Q0 in the initial state. And if I try to sit on this point P0 and also on the point Q0, and if I try to see where I am with respect to the original state, this is what we have. P0 underwent a displacement of U. That motion which it has, the object has gone for from this state to this state. See, the position, the coordinate system is fixed. The coordinate position is fixed. It is a fixed reference frame. The object originally was here, and after it underwent motion, it is here. All right. And if I concentrate on this point P0 in the final state, I'm calling it with P. If the original coordinate of this point is represented by Q0, I'm representing it by the point Q in the final state. P has underwent a deformation of U. Okay. And original length between PQ was dr0 vector, and the new PQ is represented by dr. Since P has undergone by the deformation of U, I have said, okay, then Q naught has underwent by deformation of U plus du, a small increment. dr is an infinitesimal quantity. dr, d0 is an infinitesimal quantity. du, so is that infinitesimal quantity. All right. Okay. So please draw this figure, because in the subsequent slides, I do not have this figure, and I will be talking as if you have this figure at your desk. All right. So I've drawn a shorthand version of the same. So P has undergone a deformation of U. Q has underwent a displacement of U plus du. Original length was dr0, and the final length is dr. Right. You can draw the parallelogram diagrams adding U and dr0 and make up for the other unknown vectors. So now let's start to write all the information that we know about this particular diagram. Okay, this particular diagram. Short form of this is shown here. So position vector of P0. P0, what was P0? P0's position vector is x naught I hat, y naught j hat plus z naught k hat. So that's what it is. And P is at a position vector of R, and the coordinates of P are known, which is x comma y comma z, which means the corresponding position vector of P is xi plus yj plus zk hat. Right? All straightforward things so far. So let's go to the next level. The displacement at point P0 is U. We can see this, we can read it directly from the figure. Displacement is U. And what is this displacement? It is R minus R0. Position vector of P was R, P0 was R0. So this is the displacement at point P0. And I can also always as well write it in terms of coordinates. Right? Now U, when I say U, this is basically UP, I mean displacement at point P0. Now in general, the displacement at a point is actually a function of that coordinate system. All we are saying is, if you're talking about displacement at a position vector P, if you're talking about displacement, then it is actually a function of that original position. That is all we are trying to say. I can write this last line as U r cap vector plus V r j hat plus W r k hat. Okay, so all various forms of writing the same displacement. Right. So now that we are done with position vectors and displacement vectors, let's proceed further. Let's start with this first concept of displacement gradient. What is displacement gradient? We have seen so far until now, we are able to write the coordinates and we are able to write the displacements right at point P, or you can extend the same thing to points Q and Q0. So I'm going to see the relative displacement of Q0 with respect to point P0. What is the displacement? The original length of the vector was dr0, final length is dr. So what is the relative displacement? P has gone to a distance of, gone by a displacement of u. Q0 has gone by a displacement of u plus du. So the relative displacement is du with respect to point P0. P0 underwent a displacement of u, Q0 underwent a displacement of u plus du. So this is the final displacement that you have. Now, since I know u, v, and w, I can write them in terms of the corresponding coordinates. Right? What is du? The corresponding x coordinates. What is dv? As shown. So is dw. Okay. Please do not think this as omega. This is not omega. This is w. All right. So I'm writing du in terms of the coordinates. Okay. Now that I know this, see, this looks familiar. U of x plus dx, y plus dy, z plus dz, and so on. So I'll use this, reminds me of Taylor series. So I'll use Taylor series for each of the components, and I'll neglect the higher order terms because I have only two terms. So I'll write this as the following. What is u of x plus dx0, y0 plus dy0, z0 plus dy? It is simply this expressions. Likewise, I will do the Taylor series expansions for the y and z components as well. All right. So this equation, I'm going to recast it in terms of matrices because I have dx0 common. So is dy0, so is dz0. So I'm going to write this in vectorial form as this. All right. And we have seen this quantity. Dou ux by dou x, dou v by dou x, dou w by dou x, and likewise with y and z. We have seen this quantity in when we learned tensors. So I'm going to write this as du. This is grad u and dr0. Right? Well, why am I saying 0? 0 is basically talking with respect to the initial state. Okay, so this is what I have. What are these? Du was nothing but the relative displacement. That's what we started by saying. This is the displacement gradient. And dr is the relative vector position. What was dr? dr0. dr0 was the vector q0 p0. Vector q0 p0 was dr0. Du was the relative displacement of q0 with point p0. So the relative displacements are correlated with the relative position vectors and the displacement gradients. So that is how the displacement gradient concept evolved. And hence then it follows up with other concepts. So the literature has been built by trying to relate the relative displacement with respect to the relative position vector. Okay, because in the initial state. Okay, this is our reference. With respect to the reference, if I want to understand the deformation between two original points or two known points, A and B, we are trying to write the relative deformation. Relative point A must have undergone some deformation. Point B must have underwent some deformation. We are trying to write this relative displacement in terms of the relative position. And that's how this concept of displacement gradient comes in practice. All right. Now we have seen in all the three styles. Now this displacement gradient, del u or gradient u. What is gradient u? This is actually a tensor. That's why you're able to write it in terms of matrix. So this is a tensor, right? And any tensor, I can write it as a sum of its symmetric part and antisymmetric part, given any tensor. Right? This symmetric part is called as strain. And this is the rotation vector. Rotation tensor, I'm sorry. Rotation tensor. This is omega, not W. Let me write it carefully again. This is omega. So the gradient of displacement is nothing but the sum of strain tensor and rotation tensor. The strain tensor happens to be the symmetric part. The symmetric part of the displacement gradient is referred to as a strain tensor. Or simply strain. For us, strain means the strain tensor. So I'm writing this as epsilon is equal to the symmetric part. And this is in tensor form. Right? And I can write it in component form. Is this in component form? No. This is only the component. You need to have the diode. Okay. This is a component of this particular diode. Otherwise, you are equating a tensor to a component, which is incorrect. Right? This is the correct form. Okay, you have it in the strain tensor in tensor form and in indicial form. And I will write it in matrix form as well. And this is what it is. Okay. Normally, this symmetric, if the vector or if the tensor is symmetric, you write it in the third row, first column. You write it as sim and you write the non-repeating components, which is the upper half of the triangle, upper half of the matrix, upper triangular matrix. Right. So this is the definition of strain. You have now tried to put it in every possible form: tensor form, indicial form, matrix form, and its corresponding components. Right. So symmetric parts of displacement gradient is a strain tensor. And as we are dealing with small deformations which are actually small, right? In the sense of 10 power minus 3 or 10 power minus 2 of the original length. We are dealing with such small delta-Ls. If you are thinking of a one-dimensional system, this is the order of displacements that we are looking at. Okay. The ceiling undergoes a deformation. The walls undergo some deformation, but all those are small as compared to the length of the wall or the dimensions of the wall. So we are looking at such small displacements which are infinitesimal, and hence this definition, which we have just defined, is often referred to as the infinitesimal strain tensor or simply infinitesimal strain. There are various other kinds of strains which are also in practice, but for the common engineering structures, this strain is for the kind of deformations which common engineering structures undergo. The strains are small and hence it is referred to as infinitesimal strain. Further, things which you know, normal strains are given by the diagonal elements of this strain tensor and shear strains by the non-diagonal elements. So effectively, you have 6 unique components, 3 normal and 3 shear components of strain. All right. So we will from now on use this term of infinitesimal strain. All right, now let's look at the antisymmetric part. This was the original displacement gradient. This is the symmetric part and this is the antisymmetric part. And the antisymmetric part is called as a rotation tensor. It is usually denoted by this term omega. Okay, it's also a tensor, again in tensor form expansion and in indicial form. And I'm writing its components in matrix form as well. As you see, by the virtue of our definition, it is antisymmetric. And what is antisymmetric? The corresponding components are when you take the transpose, it adds up to 0 with the original tensor. So you have 3 unique components here. Physically, what is it representing? This is the definition of antisymmetric part. For small deformations, physically, what is it representing? This is what it is representing. This rotation tensor gives the angles of rotation about the respective axis. Okay. For example, this is just a notation. Rotation in anticlockwise is taken positive. And the rotation vector, how do we identify what is the rotation vector? Given a rotation tensor, how do we identify which parts, which points are being rotated about which axis? So since it is antisymmetric, you can construct a vector from the displacement by taking the curl of the displacement. And this omega, the components of this omega vector are nothing but the elements of the rotation tensor. These are the elements of the rotation tensor. Since it is antisymmetric, the tensor calculus allows us to define an axial vector. Rotation tensor has only 3 independent components. Using those, one can construct a vector called as axial vector, and this can be derived this way. Okay, and these represent the corresponding. So if you know omega zy, which means you know the rotation about x-axis. And if the value is small, this is what we are trying to say. Since we are dealing with small deformations, which implies the rotations a point undergoes are also small. And in those cases, when the angles are small, you can approximate sin theta as theta or tan theta as theta. And that's what we are trying to say, that the component directly gives the angle. Instead of saying it is tan theta, I'm saying it is directly gives the angle. All right. So we started with an undeformed object to a deformed object. We tried to correlate the relative displacement between points to the relative position vector. And that's how the concept of displacement gradient came. And using displacement gradient, we're able to quantify, we're able to come up with two entities called as strain tensor and rotation tensor. Both of them are for us infinitesimal quantities because we are dealing with small deformations. Right. So now let's go with, now that we formally defined what strain and rotation tensors are, let us analyze each and individual point. We started this session by saying deformation, I can write it, I can quantify it as change in length along a particular direction or change in angle between two perpendicular lines, right? So that's what we will try to understand because that is what we started with. So we'll, given this diagram, we will try to identify how to write these two quantities. Change in length per unit length in any direction, right? So the same figure again. So I'll consider this segment P0, Q0. That is the initial state. PQ is the final state. So P0, Q0 became PQ, right? So we want to identify what is the change in length PQ and change in length per original length. So the final length, if it is DL and the original length is DL0, we need to identify the changes. So what I wrote, PQ is DL0, N0. So the direction of DR0 I have written as N0. The direction of PQ I have written it as N. Okay, these were the two additions as compared to our original figure, which showed the motion of an object. Everything else, every other variable was already defined. DR0 was the relative position vector. DU was the relative displacement vector, right? And U was the displacement at point P. Now I have brought in two new variables, P0, Q0. The direction of vector Q0, P0 or P0, Q0 is N0 and the direction of vector PQ is N. I am calling the length of vector P0, Q0 as DL0 and I'm calling the length of vector PQ as DL. So I'm writing the same vectors in terms of their amplitudes and unit vectors. So how do we define the strain? Since the original direction is N0, I will try to identify the change in length per unit length along N0. How do I identify if I have a vector P, if I have two vectors, vector P and vector P, how do I identify the component of vector P along vector V along vector P? It is V dot P hat, right? So first let's identify that and then identify along N dot, and then you simply need to dot it with N0, which gives you the scalar quantity. DL minus DL0 by the original length. I am identifying the change in length per original length along N0. It's not a component. I'm just doing a double line. So let me erase this. I'm trying to identify. One is the formal definition which we have seen, but I'm trying to also put it in perspective as to how does one calculate given all these vectors. To simplify it, this is what you will get. How will you get this? DL. DL. What is DL? The magnitude of the vector PQ, or basically DL is this. And how do I calculate it? I simply need to take the dot product of dr. Dr dotted with dr. Right? And then write dr in terms of dr0. Likewise, what is dl0? dl0 is square root of dr0 dot dr0. All right. So proceed in this direction. It's pure vector algebra based on this trapezium. Okay. So you start this way and you use in terms of, you just do the vector algebra and you would end up with this kind of expression. This is how the strain quantity comes out to be. The strain along a vector N0 is actually this. Okay. Strain along a vector N0. This is a higher order term. You will see I have just, if you do all the vector algebra, let me erase this. You start from DL0 as dr bar and dr and try to identify dr in terms of the remaining variables and do all this vector algebra, you would end up with this quantity. And then you would see that you will get the strain along this particular direction N0 will have this component, will have the quantity which is infinitesimal strain. Okay, so this is what we have defined. See, the deformation change in length per unit length is not limiting us in saying, no, you only deal with small deformations. It's not saying it. It is simply saying you have a final length, you have an initial length, you take the reference of it and you try to identify the difference and take the ratio. That's what we are saying, change in length per unit length along a particular direction. And when you do that, you actually even get even higher order terms depending upon what is the precision that we need. And in that process, you will figure out that this particular term is comprising of the strain tensor which we have. Okay, and this quantity represents the strain along that particular direction N0. All right, so please work out this particular part. Likewise, one can define the deformation, one can quantify the deformation in terms of change in angle between two perpendicular lines or in between any two lines. And the common way to identify angles is to either take the dot product or cross product. Okay, and so you can define two perpendicular lines at vector P0. Okay, and take the dot product, use similar extensions in vector algebra, and you would still again end up in terms of the strain tensor. All right, so this is how so regardless of whether you start in a very formal way or whether you try to stick to your definition, which is change in length by original length, you would see that the strain which we have defined does picture in. Okay, and if you can also split this expressions in by incorporating the rotation tensors as well. All right, now we have seen, we try to correlate. First we have defined in tensorial forms, and then we try to relate fallback on our old definitions, which are change in length per unit length or change in angle between two perpendicular angles, two perpendicular line segments rather. All right, then the last concept, which is on deformation gradient. We started with displacement gradient, then we defined strain tensor, rotation tensor, then we saw the change in angle and change in length business. And this is the last concept which we will come across, which is deformation gradient. What is deformation gradient? This is the deformed vector dr, which is nothing but pq. The undeformed vector was p0 q0, which is given by dr0. dr I can write using this particular triangle as dr0 plus du, right? And du, which is the relative deformation, I can write it in terms of the deformation displacement gradient and the original relative position vector dr0. I can take this as common and I'll call this as f. This f is the deformation gradient. Okay, deformation gradient relates the deformed length to the original length, whereas displacement gradient relates the relative displacement to the relative position vector. Deformation gradient relates the deformed vector to the undeformed vector. Okay, so this is also one more similar quantity, but it is correlated or it is dependent on the displacement gradient. So this quantity is the deformation gradient. And as I said, it maps the undeformed to the deformed configuration or vice versa. All right. Using displacement gradient, we have identified two kinds of tensors. One is the strain tensor and other is the rotation tensor. Using deformation gradient also, people define strains. Why should we have so many definitions? Because different materials behave in a different way. Metals behave differently as compared to polymers, and they are very different from inorganics or ceramic materials. Hence, there was a need to define things in few ways. Okay. So more definitions of strain. So are we going to use this deformation gradient? Yes and no. Yes, in the sense it can be used to define strains of other kinds. There's a strain called Green Lagrangian tensor, and it is defined this way. It is nothing but the infinitesimal strain which we defined plus this additional quantity. Where is this used? When it is used in, for an example, I can give you one quick example. It is used in area called non-destructive evaluation. When you want to identify the defect in a sample or in a specimen, in a structure or a wall, pillar, chair, pressure vessel, often when you want to identify the inhomogeneities or the cracks, you would see nonlinear measurements. If you send in a wave of particular frequency, you would get a wave of twice the frequency in the output. Your input is a wave of one frequency, whereas the output will have a wave of twice the frequency, which means there's a higher order deformation. Although you are sending in linear one, locally there is a nonlinear deformation, and that is captured by this particular term. Okay, so the Green Lagrangian strain tensor is also in use in wave mechanics to identify defects. That's one such example. Okay, if you're not dealing with not so real infinitesimal deformations, then this is one small increment to it. Likewise, there is also Cauchy deformation tensor, which is defined in terms of purely the deformation gradient. All right, so more or less all the strain quantities are defined in terms of the displacement gradient or deformation gradient. All right, so with this we will conclude this concept on strains, and we will in the next class we will continue a little more on the strains, how they can be used to quantify the deformations. Now that we've defined in an organized way, we put things systematically using diagrams and defined it, saw it in tensor form, indicial form, and matrix forms. Next class onwards, we will try to solve some problems or then see how the next set of kinematics could be dealt with. Okay, we've seen the first aspect of kinematics, which is on strain, and we'll see how this can be extended to do better things.